In 1899, the American Telephone and Telegraph Company had a secret, and the secret was this: the telephone didn't really work. Oh, it worked across town. It worked between nearby cities. By 1899, there were more than 1 million telephones in America, operators connecting calls through switchboards in every city, and the Bell companies were building what would become the mightiest monopoly in industrial history. But stretch, a telephone line passed a few hundred miles, and something strange and terrible happened to the human voice inside it. It faded, yes, every mile of copper stole a little energy, but worse than fading, it smeared. The crisp edges of consonants dissolved. Different pitches of the voice traveled down the wire at different speeds and arrived out of order, so that by the end of a long line, words arrived as underwater mush. Engineers of the day had a phrase for it: talking through a wet string. The flagship long-distance line of the era, New York to Chicago, opened in 1892, was nearly 1,000 miles of copper as thick as a pencil, one of the most expensive constructions in America per mile, and at the far end of it, a shout arrived as a whisper wrapped in fog. Boston to Chicago barely functioned. New York to Denver was a fantasy. A transcontinental Coil, New York to San Francisco, was, by the straightforward physics everyone accepted, impossible. The voice would die somewhere around the Rocky Mountains, no matter how much copper you spent. And you could not simply amplify the signal, for one crushing reason: the amplifier had not been invented yet. There was no such thing, anywhere on Earth, as a device that could make an electrical signal bigger. Whatever voice you put into the wire at New York was all the voice there would ever be. AT&T's engineers understood, with total clarity, that this was not a technical inconvenience. It was an existential ceiling. The company's entire strategy, the thing that justified the monopoly, was universal service, one network, connecting everyone coast to coast. If long-distance telephony was physically impossible, the Bell system was a collection of disconnected city networks wearing a national costume, and the telegraph, boring, reliable, long-legged, would own the continent forever. And then, between 1899 and 1900, the ceiling shattered, not with an amplifier, that was still 15 years away, not with thicker copper or higher voltage or any brute force answer. The solution was a small, dull, iron-cord ring of wire, about the size of a donut, costing a few dollars, bolted onto the line every mile or so. It amplified nothing. It added no energy whatsoever. By every intuition of every practical telephone man of the century, it should have made things worse, because what it added to the line was, of all things, more impedance. That little donut roughly tripled the reach of every long-distance line on Earth, saved AT&T a sum equivalent to billions today in copper alone, ignited one of the nastiest priority fights in the history of invention, made an immigrant shepherd boy rich and famous, left the true genius to die in poverty, and taught the modern corporation the most consequential lesson it ever learned: that abstract mathematics, pursued by people in quiet rooms, is worth more than all the copper in the world. This is the story of the loading coil, the humble component that saved the long-distance call and quietly built the 20th century's greatest research empire. To love this story, you need to understand the problem in your bones, and the problem begins with what a telephone wire actually is. When Alexander Graham Bell patented the telephone in 1876, the device itself was almost laughably simple: a diaphragm, a magnet, a coil of wire. Speech pressed on the diaphragm wiggled a current, and an identical device at the far end turned the wiggles back into sound. The miracle was that it worked at all. The entire power carrying your voice was the microscopic energy of your own breath, converted to electricity. Nothing boosted it. Nothing could. Over short distances, that was fine. The trouble emerged as the wires stretched, and it emerged in two distinct flavors. The first, everyone understood: resistance. Copper steals energy from a current, mile after mile, turning your voice into heat. The 19th century answer was equally understandable: use more copper. Long-distance lines grew to absurd thicknesses. The New York-Chicago line used wire weighing hundreds of pounds per mile, and copper became the single greatest cost of the entire telephone enterprise. Roughly half the capital of the Bell system, it was said, hung on poles between cities. The second flavor was the killer, and almost nobody understood it, because it lived in mathematics the telephone industry didn't read. A pair of wires is not just a resistance, it is also, inescapably, a capacitor. The two conductors, separated by air or insulation, store charge between them, and every foot of line adds more of this capacitance. To the rapidly wiggling currents of speech, that distributed capacitance acts as a continuous leak, high frequencies draining away faster than low ones, and more insidiously, it makes different frequencies travel at different speeds. A voice is a chord of many frequencies. Send that chord down 500 miles of capacitive line, and it arrives as a smeared arpeggio. The treble weak and early decayed, the timing scrambled, the consonants, which live in the high frequencies and carry nearly all the intelligibility of speech, gone. The line didn't just weaken your voice, it unspoke it. Underground and undersea cables, where the two conductors lie close together with insulation between, were catastrophically worse. Their capacitance per mile was many times that of open wire on poles. This is why, decades earlier, the first transatlantic telegraph cables of the 1850s and 60s had been such heartbreak. Even simple dots and dashes smeared into one another, and operators had to send so slowly that a short message took hours. The telegraph could at least slow down. The human voice cannot slow down. Speech happens at the speed of speech, and if the line cannot carry that speed, the line cannot carry a conversation at any price, at any patience. By the 1890s, the best minds in the industry had converged on a grim consensus. Attenuation and distortion were facts of nature, to be fought with copper and endured with squinting ears. The idea that the problem had already been solved, completely, elegantly on paper, by a deaf, unemployed, self-taught Englishman working alone in a stone cottage in Devon, funded by nobody, employed by no one, would have struck them as a joke. His name was Oliver Heaviside, and he is one of the greatest scientists most people have never heard of. Oliver Heaviside was born in London in 1850 into poverty, partial deafness from childhood scarlet fever, and a temperament that made enemies of institutions on contact. He left school at 16. He never attended a university, never held an academic post, and for most of his life, never held a job at all. He taught himself mathematics and physics with a ferocity that still startles historians, and then, from rented rooms and borrowed cottages, he quietly rewrote the science of electricity. It was Heaviside who took James Clerk Maxwell's monumental, nearly impenetrable equations of electromagnetism, 20 equations in 20 variables, and compressed them into the 4 elegant vector equations every physics student now learns as Maxwell's equations. Maxwell wrote the symphony, Heaviside arranged it for orchestra. He invented much of the mathematical toolkit of modern electrical engineering, coined the words inductance, impedance, and conductance, predicted the ionosphere layer that still bears his name, and did it all as an outsider, publishing in trade journals, feuding with the scientific establishment, living on his brother's charity, and eventually a grudging government pension. And in the 1880s, working through the physics of telegraph and telephone lines, Heaviside solved the smearing problem, completely, on paper. His transmission line theory, published in 1887, described a line by 4 quantities per mile: resistance, capacitance, leakage, and inductance. The mathematics revealed a hidden harmony, distortion. The smearing that murdered long-distance speech was not inevitable at all. It arose from an imbalance among the 4 quantities. If the line's inductance were increased, deliberately, artificially, until it balanced the capacitance in a precise ratio, the line became what Heaviside called distortionless. Every frequency would travel at the same speed and fade at the same gentle rate. A voice would arrive faint, perhaps, but perfect, a whisper instead of a mumble, and a whisper you can work with. Read that again, because every practical man of the era got it backwards. The cure for the telephone line was to add impedance to it. Loading the line with coils of wire, chokes, the sort of thing intuition said would strangle the signal, would actually free it. Heaviside published the result, explicitly suggested that inductance could be added artificially, and even sketched the benefit for telephone circuits. It was the complete answer, a decade early, free for the taking. Nobody took it. The reasons are a case study in how knowledge fails to travel. Heaviside's mathematics was forbidding, his prose was thorny, and he had spent years in open warfare with William Preece, the politically powerful chief engineer of the British Post Office, who believed, wrongly but officially, that inductance was the enemy of clear transmission. Preece's institutional weight buried the idea in Britain. Heaviside, characteristically, refused to patent, refused to lobby, refused to translate himself into the language of money, and went back to his equations. He would live to see other men win fortune and fame for the practical application of his theorem, and when one of them was later praised in his presence, Heaviside's response had the bite of a man keeping score. He noted, correctly, that the idea had been his, in print, years before. For the idea to change the world, it had to cross the Atlantic and find two men who could read Heaviside's mathematics and see dollars in it. It found them almost simultaneously, and that simultaneity is where our story turns into a race. Michael Pupin's life story is so perfectly American that, when he finally wrote it down, it won the Pulitzer Prize. Born in 1858 in a Serbian village in what was then the Austro-Hungarian frontier, Idva, a place, he liked to say, that could be found on no map, Pupin herded oxen as a boy, learned to signal across fields by knocking on the ground, the way herders sent messages, and absorbed from his illiterate mother a reverence for learning he carried like a religion. At 15, he emigrated. He landed at Castle Garden, New York, in 1874, with, by his own famous accounting, 5 cents in his pocket, no English, and no acquaintances on the continent. He spent 5 years in boiler rooms and farm fields, learned English from newspapers and night classes, and in 1879 talked his way into Columbia College, where he proceeded to win essentially everything: honors, fellowships, study in Cambridge and Berlin under Helmholtz himself, and by 1889, a faculty post back at Columbia teaching the new science of electrical engineering. Pupin was that rare combination, a genuine physicist with a showman's instincts and a hustler's nose for value. In the late 1890s, he turned to the great unsolved money problem of applied electricity, long-distance telephony, and he did what the practical telephone men had never done. He read the theory. He read Heaviside. And where the industry saw impenetrable mathematics, Pupin saw an engineering recipe missing only one number. Heaviside had shown that added inductance would cure distortion, but adding inductance continuously, wrapping the entire line in iron, was hopelessly expensive. The practical question was, could you add it in lumps, discrete coils, spaced along the line like beads on a string? And if so, how close together did the beads have to be before the line stopped noticing they were lumps? Pupin's answer, worked out in 1899 and published in 1900, was the piece that made the theory buildable. Drawing an analogy he credited to watching a vibrating string, weighted at intervals, behave like a heavier uniform string, he derived the spacing rule. The coils must be spaced a small fraction of the wavelength of the highest speech frequency on the line. In practice, a coil roughly every mile or so on open wire, closer on cables. Satisfy that rule, and a lumpy line behaves like Heaviside's smooth, distortionless one. Violate it, and the coils become walls the signal cannot pass. He wrapped the result in patents, filed in December 1899, with the instincts of a man who had arrived with 5 cents and did not intend to return to that condition. What Pupin did not know, and what makes this story delicious, is that at that very moment, inside AT&T itself, a quiet company theorist had already solved the same problem, had derived the same spacing rule with more rigor, had actually built the coils, and had proven them on real telephone circuits, working speech, through loaded lines, in laboratory and field. His name was George Campbell. He had everything except a filed patent, and the reason he didn't have one is the kind of corporate blunder that gets taught for a century. George Ashley Campbell was everything Pupin was not. A New Englander of quiet means, MIT, Harvard, and Göttingen educated, mathematically deep, personally reticent, and employed, since 1897, in the Boston engineering department of the Bell system, in a tiny group with a radical mandate: apply real mathematics to the telephone plant. Campbell was, in effect, one of the first true theoretical engineers ever put on an American corporate payroll, and the loading problem was his first great assignment. Working from the same Heaviside foundations, Campbell derived the lumped loading condition, the Coil spacing rule, in 1899, with a rigor historians of science generally judge superior to Pupin's. But he went further because he had what Pupin lacked: a company's resources and real telephone circuits. Campbell designed practical coils, iron-core toroids, worked out their winding and placement, and in the autumn of 1899 tested them on actual cable circuits, demonstrating clear speech through lines that had been unusable. By any engineering standard, Campbell had not merely conceived the loading coil, he had reduced it to working practice while Pupin was still writing. Then came the blunder. Campbell urged a patent filing. The Bell system's lawyers and managers, in a display of institutional caution that would cost them dearly, deliberated. There were internal reviews. There were questions about whether the invention was patentable over Heaviside's publications. Weeks passed. Campbell's patent application finally went in early 1900, weeks after Pupin's December 1899 filing. In the interference proceeding that followed, the fight inside the patent office over who invented first, the record showed Campbell with the earlier and better reduction to practice, Pupin with the earlier filing date, and crucially, a lucid, self-promoting account of conception. The examiners, and ultimately the courts, awarded priority to Pupin in 1904. Engineers inside Bell were bitter about it for decades. Historians have chewed the verdict ever since, with most concluding that Campbell had the stronger technical claim and Pupin the stronger paperwork, and that Heaviside, hovering above them both, had the strongest claim of all and no paperwork whatsoever. Now watch what AT&T did next, because it reveals the cold clarity that built the Bell empire. Rather than litigate forever against a patent it might not beat, AT&T simply bought Pupin. An initial payment reported at $185,000 for the patent rights, with royalties that eventually totaled some $455,000, several million in modern money, one of the largest sums ever paid to an academic inventor to that date. Pupin became rich, celebrated, a Columbia legend, later a Pulitzer-winning memoirist, and a founding father of American science policy. Campbell got a raise, a career, and the department he'd pioneered. His consolation prize, as we'll see, turned out to be the invention of an entire branch of engineering. Heaviside got nothing, declined an offered honor or two with magnificent scorn, and died in 1925, alone, in a Devon cottage with granite furniture, nursed occasionally by neighbors, the greatest electrical theorist of his age. 3 men, 1 idea: the outsider who discovered it, the corporate theorist who built it, the immigrant who sold it. Every technology story you will ever hear contains these 3 people. Rarely do they come this cleanly separated. And the idea itself. The idea was about to earn back its price roughly 100,000 times over. Let's open the little iron donut and understand, honestly, what it does, because the physics is beautiful and almost nobody ever explains it. Picture your voice as a crowd of runners released down a long corridor, each runner a different frequency. Deep vowels are the slow, heavy runners. Crisp consonants are the light, fast ones. On a perfect line, all runners hold formation, and the crowd arrives at the far end in the same order it left. Your words, intact, merely quieter. The telephone line's capacitance ruins the race. Capacitance acts like sticky mud along the corridor floor, and here's the cruel part: it's stickier for some runners than others. The formation dissolves, runners arrive out of order, exhausted, some barely at all. That's the smearing, the wet string. More copper widens the corridor, less resistance, but does nothing about the mud. What Heaviside's mathematics revealed is that a line has a second personality: inductance, the magnetic sluggishness of current, which behaves like a kind of flywheel attached to each runner, resisting changes in pace. And the miracle hiding in the equations, the distortions caused by capacitance and by inductance pull in opposite directions. Tune the amount of inductance so it balances the capacitance. The famous Heaviside condition and the two imperfections cancel. The mud is still there, the flywheels are still there, but every runner now feels exactly the same total handicap, and the formation holds. The line still weakens the voice, nothing adds energy, but it weakens every frequency identically, and a uniformly faint voice is a clear voice. Human ears and later amplifiers handle faint, nothing handles scrambled. The loading coil is simply the flywheel, sold in lumps. A ring of iron wound with the line's own wire, installed in series every standard interval, historically about every 6,000 feet on cable circuits. Pupin's and Campbell's spacing rule says the lumps must come frequently enough that the slowest important frequency never travels far without feeling one. Satisfy it, and the lumpy line imitates the ideal smooth one almost perfectly. On the pole routes and under the streets, the coils lived in sealed iron parts, dozens of coils per part, one per circuit pair, and lineworkers learned to spot the parts hanging like fruit along the long-distance routes. The physical signature of mathematics, repeated every mile from New York to everywhere. The numbers the donut delivered still astonish. On loaded circuits, usable range multiplied roughly threefold or more overnight. Routes that had demanded pencil-thick copper now worked on wire half the weight, and AT&T's engineers calculated the copper savings alone, by the mid-1920s, at around $100 million, comfortably exceeding, by itself, the entire cost of every research laboratory the Bell system had ever operated. New York to Denver opened in 1911 on loaded lines, over 2,000 miles, still without any amplification whatsoever, the human breath alone, chaperoned by iron donuts, crossing 2/3 of a continent. One fact deserves its own sentence, for every viewer who has ever been told that progress comes from adding power. The greatest single leap in the history of telecommunications range was achieved by a passive lump of iron that added nothing, amplified nothing, and consumed nothing, but merely made the medium honest. And yet the donut had limits, sharp ones, and the story of those limits is the story of how the modern electronic age began. By 1909, the loading coil had carried the human voice as far as passive physics would allow, and AT&T's new president, Theodore Vail, made a promise calculated to terrify his own engineers. The company would open a telephone line from New York to San Francisco in time for the Panama Pacific Exposition of 1915, 3,400 miles. The best loaded line in existence managed 2,000 and arrived at Denver as a whisper balanced on the edge of hearing. The last 1,400 miles, over the Rockies and the deserts, needed something the world did not yet contain: amplification. The candidate arrived from the strange margins of invention. Lee De Forest, a showman inventor perpetually one step ahead of his creditors, had in 1906 added a third electrode, a zigzag wire grid, to the Fleming valve, creating a vacuum tube he called the audione. A small voltage on the grid controlled a larger current through the tube, the first device in human history that could make an electrical signal bigger. De Forest himself only half understood it. His audiones were gassy, fragile, temperamental things, useful mainly for radio detection. But in 1912, his associates demonstrated the audione to AT&T as a telephone repeater, and the company's new research chief, Frank Jewett, and his physicist Harold Arnold saw through the flicker to the future. Arnold diagnosed the flaw immediately. The tube needed a far harder vacuum. AT&T bought the telephone rights to the audione for $50,000. De Forest, broke as usual, took the money, and Arnold's team rebuilt the device into an industrial instrument, the high-vacuum triode repeater. Now watch the two inventions work together, because this is the architecture of every network built since. The loading coils kept the line honest, all frequencies marching in step, so that what arrived at each repeater station was faint but undistorted. The vacuum tubes at stations along the route, Pittsburgh, Omaha, Salt Lake City, lifted the faint signal back to strength and sent it onward. Purity from the passive iron, power from the glowing glass. Neither alone could cross the continent. Together, on June 17, 1914, the circuit closed, and on January 25, 1915, in the formal ceremony, Alexander Graham Bell himself in New York spoke into a replica of his 1876 instrument the same words he had once called to the next room. "Mr. Watson, come here, I want you." And Thomas Watson, 3,400 miles away in San Francisco, replied that it would take him 5 days this time. The call was a sensation, and the accounting behind it tells the deeper story. The transcontinental line used some 2,500 tons of copper, 130,000 poles, 3 vacuum tube repeater stations, and loading coils by the thousand along its eastern sections. A 3-minute call cost $20.7, several hundred in today's money, and there was a waiting list. Within a decade, improved repeaters had made the loading coils on the longest routes optional. Within 2, carrier systems, sending many conversations over one pair at high frequencies, made them, on those routes, an obstacle. The little donut had carried the network to the edge of the electronic age, and the electronic age, with perfect ingratitude, immediately began scheming to remove it. But before that reversal, the coil delivered its most important cargo, which was not a voice at all. It was an idea, delivered directly into the boardroom of AT&T, mathematics pays, and that idea built the most productive laboratory in human history. Corporations, like people, are shaped by their formative windfalls. The loading coil was AT&T's, and the company never forgot the arithmetic. Consider what the ledger showed by the early 1920s. On one side, the salary of George Campbell and a handful of theorists, the $455,000 eventually paid to Pupin, and the modest cost of iron and wire. On the other, roughly $100 million saved in copper alone, whole categories of service, urban cable networks, interurban lines that were otherwise physically impossible, and the competitive moat of patents that had helped the Bell system consolidate its monopoly through the fiercest competitive era in its history. No investment in the company's history, arguably in American industrial history to that point, had returned so much on so little, and its source had not been a heroic tinkerer in the Edison mold, but a man at a desk, reading Heaviside, doing mathematics. AT&T institutionalized the lesson with the thoroughness of a religious conversion. Campbell's Little Boston Theory Group grew into the engineering departments of Western Electric. In 1911, Frank Jewett consolidated research under one roof, and on January 1, 1925, the whole apparatus was incorporated as Bell Telephone Laboratories. Bell Labs would go on to produce the transistor, information theory, the solar cell, the laser's foundations, Unix, and 9 Nobel Prizes, and every history of it that traces the founding logic arrives at the same origin story the employees themselves told. The loading coil proved that fundamental research was not philanthropy. It was the highest margin product the company made. Campbell himself furnished the second proof. Denied the loading coil patent, he kept pulling on the mathematical thread it had given him, the behavior of lines with periodic lumps, and noticed that a loaded line's sharp cutoff frequency, the pitch above which signals simply die, was not only a limitation. Deliberately designed, it was a tool, a circuit that passes some frequencies and blocks others. In 1915, he invented the electric wave filter, the bandpass filter, and with it the possibility of stacking many conversations on one wire at different frequencies. Carrier multiplexing, the ancestor of every channel, every band, every slice of spectrum in the modern world. Radio, broadcasting, FDM telephony, and ultimately the layered frequencies of your Wi-Fi all descend from Campbell's consolation prize. Historians of engineering rank the wave filter among the most important inventions of the century. Campbell, characteristically, published quietly and let others build the empires. Pupin, meanwhile, became the century's model of the celebrity scientist, Columbia's grand professor, founding member of the National Advisory Committee for Aeronautics, the body that became NASA, president of learned societies, confidant of governments, and with his 1923 autobiography From Immigrant to Inventor, a Pulitzer Prize winner whose life story, Oxcarts to Oscillographs, became required reading for a generation of American schoolchildren. The book barely mentions Campbell and treats Heaviside generously but vaguely. Winners write memoirs, theorists write papers, and hermits, as we're about to see, write letters to posterity from cottages with granite furniture. The Coil, in short, built far more than telephone lines. It built the institution that built the information age, and it taught every corporation that copied Bell Labs, which was eventually all of them, that the shortest path between mathematics and money is often a straight line. There remained only the small matter of the three men's endings and the strange afterlife of the donut itself, which is still being hunted down and ripped out of the walls of the internet to this day. Every engineering bargain has fine print, and the loading coil's fine print eventually rewrote the whole deal. The coil's magic, remember, was a trade. It flattened distortion across the voice band in exchange for behaving like a wall above it. A loaded line is a low-pass filter. The standard configurations passed frequencies up to roughly 3.5 kHz, ample for speech, whose intelligibility lives below 3, and executed everything above with bureaucratic efficiency. In 1905, that ceiling cost nothing. There was nothing above 3.5 kHz anyone wished to send. The coil also slowed signals measurably, adding delay across long routes, and its iron core, driven hard, added its own subtle distortions, details, footnotes, until the world changed twice. The first change came fast, carrier telephony. By the 1920s and 30s, engineers wanted to stack multiple conversations on one wire pair by shifting them up to higher frequencies, 10, 20, 40 kHz, exactly the territory the loading coils walled off. On routes destined for carrier systems, the coils came out, replaced by the vacuum tube repeaters that could now amplify honestly across wide bands. The long-haul network gradually deloaded through mid-century as coaxial cable, microwave relay, and eventually optical fiber took the intercity traffic. The donut retreated to the place it had never left, the local loop, the last few miles of copper from the exchange to homes, where millions upon millions of coils sat in their pots and manholes and pole-mounted cases, faithfully flattening the voice band, bothering no one. By the 1980s, they were infrastructure in the purest sense, invisible, uncounted, immortal. The second change is the punchline of the century. In the 1990s, engineers discovered that ordinary telephone copper, the humble twisted pair, could carry megabits of data if you used the frequencies above the voice band, 25 kHz to a megahertz and beyond. The technology was DSL, the digital subscriber line, the thing that first brought broadband internet to hundreds of millions of homes over wires installed for Theodore Vail. And what stood, implacably, between those homes and the internet? The loading coil. The exact device that had saved the telephone network now blocked its future. A low-pass wall built precisely across DSL's spectrum, doing in 1999 exactly what it was designed to do in 1899, to the ruin of everyone involved. So began one of the strangest maintenance campaigns in industrial history, the Great Unloading. Telephone companies worldwide sent technicians to hunt down and physically remove coils their grandfather's generation had installed, splicing out the pots in manholes, on poles, in basement terminal boxes, guided by circuit records that were often a half-century stale and famously wrong. The industry term was conditioning the loop. Any subscriber more than a few kilometers from the exchange in the DSL era whose broadband mysteriously refused to work stood a fair chance of being haunted by Pupin and Campbell personally. One forgotten coil, anywhere in the line, and the megabits died at the voice band's edge, just as the mathematics commanded. Coils were still being discovered and extracted well into the 2010s, and in aging copper plants, a few assuredly remain, patient iron ghosts of 1900, still filtering, waiting. There is no cleaner illustration in all of engineering of the great law of infrastructure. Nothing is as permanent as a perfect solution, and nothing ages into an obstacle so completely. The loading coil saved the network for a century, then had to be surgically removed from it, donut by donut, so the century that followed could happen. Which leaves only the three men and the final settling of history's accounts. History settled with each of the three men according to his nature, which is another way of saying, unfairly, in every direction. Oliver Heaviside's last decades read like tragic folklore because they were. He grew poorer and stranger in his Devon cottage, painting his nails, replacing furniture with granite blocks, signing letters with the invented title WORM. His genius was never quite forgotten by those who mattered. The Young Institution of Electrical Engineers awarded him its first Faraday Medal in 1922, and a delegation once traveled to his cottage to deliver an honor he received with courteous disdain. When admirers mentioned the fortunes made from loaded lines, his reply was a shrug wrapped in acid. The theory had been given to the world freely, and if the world chose to pay the wrong man, that was the world's arithmetic, not his. He died in February 1925 after a fall from a ladder in a nursing home in Turkey. No wife, no children, no estate, and a scientific legacy that has only grown every decade since. Modern physics and engineering honor him in the most durable currency there is, the vocabulary. Every time an engineer says inductance or impedance, Heaviside collects. Michael Pupin died in March 1935, a national figure, laden with medals, memorialized in the naming of Columbia's physics building, Pupin Hall, where in the basement a few years later, the Manhattan Project's earliest experiments would run, mourned by governments on 2 continents. His Oxcart laboratory life still assigned reading in American schools. The fine print arrived posthumously. Historians re-examining the loading coil's paper trail concluded, with increasing bluntness across the 20th century, that his memoir had inflated his originality, that Campbell's work was independent, prior in practice, and technically superior, and that both men stood on Heaviside's published shoulders. None of which erases what Pupin genuinely was, a fine physicist, a great teacher, and the most effective ambassador science ever sent to the American public. But the invention that made him famous is now, in careful histories, always credited with an asterisk. George Campbell outlived them both, retiring from Bell Labs in 1935 and dying quietly in 1954. His revenge, if a man that reserved can be said to have taken one, was total and characteristically silent. The wave filter and the mathematics of networks he pioneered became the foundation of the communications age. The profession's highest honors, the Iron Medal of Honor among them, found him despite his best efforts at invisibility. And inside the engineering literature, the lumped loading formula is as often as not called Campbell's. Bell Labs' own historians, with a candor rare in corporate chronicles, eventually stated plainly that the company believed Campbell to be the true inventor, and that the patent had been lost to lawyerly delay, a sentence that has been taught to generations of corporate patent counsel since, usually with the word never attached. 3 verdicts then: fame chose the storyteller, money chose the filer, and the engineering itself, the equations that still describe every transmission line on Earth, chose, as it always eventually does, the men who wrote them. There's one more account to settle, ours. What does a century-old iron donut have to say to the fiber optic present? More, it turns out, than almost any machine we've covered. Strip the names away, and the loading coil story is a set of permanent lessons about how technology actually advances, each one still operating, right now, in every industry you can name. Lesson 1, the bottleneck is usually understanding, not capability. In 1899, no new material, no new manufacturing process, no new component made the loading coil possible. Iron and copper wire had existed for a century. What was missing was comprehension. The industry did not understand what a transmission line was. The entire long-distance problem, the wet string, the impossible transcontinental call, was, in the deepest sense, a reading comprehension failure. The answer sat in published equations for 12 years, while a whole industry spent fortunes on thicker copper. Modern equivalents are everywhere. Every field carries unread Heavisides. The cheapest infrastructure investment on Earth remains a person at a desk who actually understands the mathematics. Lesson 2, intuition is a compass that fails near the poles. Every practical telephone man knew that adding impedance to a line must worsen it, the way every aviation analyst knew big wings meant agility, and every admiral knew 30 men couldn't run a submarine. The counterintuitive fix, add the very thing that seems like the problem, appears throughout engineering: reactive power, negative feedback, vaccines. Institutions that punish counterintuitive proposals are institutions that have decided, in advance, to buy their future from competitors. Lesson 3. The credit system measures paperwork, not truth. Heaviside published, Campbell built, Pupin filed, the money and the fame followed the filing. This wasn't a scandal, it was the system working exactly as designed, and it still works that way. Patent law rewards the person who translates knowledge into claims, which is a genuinely valuable act. But every organization that reads this story draws the same conclusion AT&T's lawyers drew in 1900, one January morning too late. When your theorist tells you to file, file. Lesson 4, the deepest one: infrastructure outlives its assumptions. The coil was installed under the assumption, perfectly correct, that nothing above 4 kHz would ever matter on a local telephone line. The assumption held for 90 years, longer than any technology plan in history, and then the internet arrived, and a million buried donuts turned from foundation to blockade overnight. Every network being built today, fiber topologies, cloud architectures, power grids, encodes assumptions its builders believe eternal, and some technician in 2110 will curse them, kneeling in whatever replaces a manhole, extracting our era's perfect solutions one by one. And a fifth, gentler lesson for the audience of this particular channel: the great machines get the documentaries, but the components run the world. We have spent this series with Concords and Blackbirds and titanium submarines, machines you can stand under and weep. The loading coil is their opposite, a device with no silhouette, no museum hall, no roar, produced by the million, installed by workmen who never knew what it did, and it is entirely possible that no artifact in this whole series changed as many lives. Somewhere between the monument and the donut lies the true history of technology, and it is mostly donuts. One story remains, the last one, where we put the coil in your hand and say goodbye to the century it built. Hold one in your hand if you ever get the chance, at a surplus store, a ham radio flea market, a telephone museum. A loading coil is unimpressive on purpose, a ring of iron alloy wound with a few hundred turns of fine wire potted in tar inside a small canister, built to be bolted somewhere dark and forgotten for 100 years. No moving parts, no power, no light. It is, by every measure a museum curator uses, nothing. Now weigh what it did. It carried the human voice across the first 1,000 miles that mattered, decades before amplification, on breath alone. It saved the world's telephone systems, the modern equivalent of billions in copper. And with that money, and the lesson of how the money was made, it seeded Bell Labs, the institution that then produced the transistor, information theory, and the operating system this video was edited on. Its patent fight wrote case law and corporate folklore that still governs how ideas become property. Its mathematical descendants, Campbell's filters, run in every phone, every radio, every Wi-Fi chip within reach of you right now, trillions of filters, all children of the donut. And when its long century finally ended, it exited history the way only true infrastructure can. As an obstacle, pried out of the internet's path one manhole at a time, still working perfectly, guilty of nothing but outliving its assumptions. 3 men gave it to the world, and the world paid them in 3 currencies. The recluse got the truth. Heaviside's equations are the ones we still use. The builder got the future. Campbell's filters became the modern world's plumbing. The storyteller got the glory. Pupin's name is on the building and the Pulitzer. If the division seems unjust, notice that each man, offered the others prizes, would probably have declined them. Heaviside did not want Columbia's marble. Campbell did not want the memoir's spotlight. Pupin, who had arrived at Castle Garden with 5 cents, wanted exactly what he got, and earned no small part of it. Invention is not 1 act but 3, discovery, construction, persuasion, and history's ledger, for once, paid all 3 accounts in full, just never to the same address. And maybe that's the note to end our story on, because this series has been asking one question in many costumes: why do the machines that change everything so rarely reward the people and institutions that make them. The Concord answer was politics. The Sun Microsystems answer was identity. The loading coil answer is the oldest and most honest one, because a breakthrough is a relay race, and the anchor leg gets the medal. The mathematics came from a cottage in Devon, the coils from a lab in Boston, the patent from an office at Columbia, the money from Broadway, and the benefit, the actual delivered benefit, came to everyone who ever picked up a telephone and heard, clear across a continent, a voice they loved, unsmeared, undrowned, arriving in perfect order, syllable after syllable, mile after mile, donut after patient iron donut. Mr. Watson, come here, I want you. It took 39 years, one genius nobody read, one engineer nobody thanked, one immigrant everybody celebrated, and several 100,000 iron rings, but Watson finally heard it from the other side of the world and answered. Thanks for watching. If you enjoyed this journey off the flight line and into the wiring, the rest of our series, The Machines, the Empires, the Impossible Designs, is on screen now. Subscribe, and I'll see you in the next story.